Well, okay, we can start with the April session of the young seminar of SIFS, of the Italian Society of Statistical Physics, and the first speaker is Duilio De Santis, and 3 years ago Duilio got a master degree in physics at the University of Palermo, working with Gioacchino Massimo Palma, and the title of the thesis was Generation of Sine-Gordon breathers in long Josephson junctions, and since then he's finishing his PhD at the same university with Davide Valenti, and today Duilio is going to speak about dynamical sine-Gordon solitons, emergence and detection. So please, Duilio, you have 25 minutes.
Okay. Thank you so much for the kind introduction. So, sorry. Okay, so thank you again for inviting me to give this seminar. So it's a great pleasure to be here. So yes, today I'm going to be discussing about these dynamical sine-Gordon solitons. They're also known as breathers, and in particular we're going to be discussing about how, in a sense, to create these solitons and how to probe their dynamics in physical systems. So the overview of my seminar is the following. So we're going to start with quite a general introduction about what a soliton is and what the sine-Gordon model is. We're going to see a bunch of applications, and then I'm going to move to some recent results that I got with my group in Palermo about this emergence of breathers and their detection, and in particular how noise, stochastic noise, can help us achieve some hard, solve some hard problems in the detection of these nonlinear modes. So let's start by reminding ourselves what a soliton is. So let's say, according to Wikipedia, a soliton is a nonlinear and stable nonlinear wave, which has the remarkable feature of preserving its shape while propagating. You might be familiar with hydrodynamical solitons, but there are actually many kinds of solitons, and their remarkable properties are due to, let's say, a balance between nonlinear and dispersive effects that we can have in various systems. So due to this, in a sense, cancellation between nonlinearity and dispersion, we can have the emergence of these remarkable objects. So nowadays the concept of soliton is widespread. For example, we have applications in fiber optics, but also in biological systems, in material science, in magnetic systems, in high energy physics. So really there is a lot of interesting research going on about these nonlinear waves, which have quite remarkable properties. So solitons were discovered actually in the 1800s by an engineer, John Scott Russell, who was studying some boat engineering problem, and he noticed this remarkable wave which would go on and on without, let's say, dissipating. So he was very fascinated by that, and since then we have a lot of research going on about these solitons. So here, for example, I show you a very famous picture about regarding hydrodynamical soliton. This ripple that you see here forming in this canal is actually an hydrodynamical soliton. And actually, this is a quite interesting picture, which was taken at a famous workshop or conference about solitons. Actually, many contributors to the soliton theories can actually be identified in this picture here, enjoying the soliton view. So the sine-Gordon model is one of the most important models where we can study solitons, and in its simplest form, the sine-Gordon model is a classical nonlinear wave equation. So you can see in the left-hand side we have this kind of wave equation terms, and on the right side we have a source term. And we typically consider a one-dimensional system, so this field phi is a function of space and time, and essentially this is a nonlinear generalization of the Klein-Gordon equation. So instead of taking phi in the right-hand side, we take sine of phi, and so this is why the equation is called sine-Gordon. So there is an interesting mechanical analog for this system, which kind of emphasizes the fundamental nature of this model. This is actually this equation is actually describing a chain of pendula coupled through elastic springs. So essentially, in this mechanical analog, phi would be the angle of rotation about the vertical axis. So that's quite a useful analog. So what kind of solutions can we find for this nonlinear equation? Well, the first thing we can do is take the linear limit of the sine, and we'll essentially find linear waves or plasma waves in some contexts. And you can find a dispersion relation for these plasma waves, and what you'll find is that you cannot have plasma waves propagating at a frequency omega which is less than 1. So there is a so-called plasma gap, and this is very important for the study of dynamical solitons. So going into the nonlinear regime, we can have solitonic solutions. So the simplest kind of solitonic solution is the so-called kink or anti-kink, and this is a topological excitation, meaning that you can assign a topological charge to this step-like object, and essentially this, as we will see, can be interpreted as a 2π rotation of the pen in the mechanical analog. And you may note that this object has some relativistic flavor to it, and well, that's due to the relativistic structure of the sine-Gordon theory. More interesting, more complex, I would say, kind of solitonic solutions are breathers or dynamical solitons. So in this case, we can understand the breather as a bound state between a soliton and anti-solitons. So these objects are non-topological because the total topological charge is 0. And what's interesting about them is that they populate the so-called plasma gap, so their frequency must be less than 1. And if we can visualize a breather, essentially it will be localized, strongly localized in space, and it will oscillate in time. That's why this is called a breather. And essentially, here I'm showing you a stationary breather, but these things can actually move, so you can have a breather with a finite velocity as well. So to summarize what we have learned so far, the sine-Gordon model has a full spectrum of periodic solutions, and for frequencies above 1, we can have phonon-like extended modes or plasma waves, and in the plasma gap, so for frequency below 1, we can have nonlinear modes known as breathers or dynamical solitons. So let's visualize them, these modes, into the mechanical analog. So as I was saying before, the kink will look like a 2π twist in the chain of pendula, and this is an animation showing a topological soliton moving around the chain. Instead, a stationary breather would look like this. So it's a localized oscillation of these pendula, and breathers are called dynamical because even if they don't move, even if they have no translational degree of freedom, they still have some dynamics to them. They still oscillate, which is something that kinks, for example, do not have. So they have this additional degree. So breathers have this additional degree of freedom, which is quite interesting in view of applications, for example. So the typical point of view for studying sine-Gordon solitons, and in particular solitons in, let's say, non-integrable scenario, so in a scenario where we have, for example, dissipation, for example, some external drive, the idea is to study perturbed soliton dynamics. So we imagine that due to the remarkable stability of solitons, we can still talk about soliton modes even in non-integrable situations. And the idea is to study how different perturbations affect the dynamics of our solitonic modes. For example, it's well known that if you have a kink or an anti-kink, depending on the topological charge, we know that dissipation slows them down. Essentially, they slow down like particles do in the presence of dissipation. And also, if you apply a constant force to a kink, or to an anti-kink, you will accelerate them. And in particular, they will go in opposite directions due to their opposite topological charge. For breeders, perturbative analysis are generally speaking more complex because it's a composite solitonic mode, but what is well known is that in the presence of dissipation, breeders are no longer stable. So the oscillation I was showing you before will die out in time over a time scale which is the inverse of the dissipation coefficient. Instead, what is known is that when you apply a constant force, you can actually break up the bound state. You can actually, by accelerating the kink and the anti-kink in opposite direction, the idea is that this phenomenon will lead to the breakup of the breeder. And so these are properties that can be also observed in experimental platforms, of course. So a physical system, which is very important for my research activity, is the Josephson junction. So a junction which is made by sandwiching a thin insulating layer between two superconducting materials. Well, we know that superconductors can be described through pair wave functions, and in particular the physics and the dynamics of these devices are essentially governed by the phase difference phi between the macroscopic wave functions which characterize the superconductor 1 and 2. So you can actually derive these two very simple and famous equations governing currents and voltages in the system, and they are called the Josephson equation. And you can see that essentially the sign of the phase difference will give us the supercurrent within the junction, and the time derivative of the phase is related to the voltage. So we can have this essentially physical quantities which are driven by the phase difference, and that's very interesting. So let's say this is for, let's say, a point like junctions, but what we can do is consider extended systems. So in a sense, we can show that if there is essentially a length parameter L and a width parameter W of a junction, and we can show that if the length and the width are respectively much larger and much smaller than a characteristic Planck scale that is called the penetration depth, then we can combine the Maxwell equations with the Josephson equations, and we get some one-dimensional partial differential equation governing the dynamics of the system. And this partial differential equation turns out to be the sine-Gordon equation. In particular, as I was mentioning before, in real physical systems, we typically have additional terms. The red one, for example, is some dissipation, and the blue one is some external force, which would be essentially an electrical bias in this case. So the units here are, the relevant length scale here for space is essentially this penetration depth lambda j I was mentioning, and the characteristic time is essentially the inverse of the plasma frequency that you can define for the junction. And we can study different geometries. For example, on the left, I'm showing you the so-called overlap geometry, which actually corresponds to Neumann-type boundary conditions for this sine-Gordon equation. But we also can study other geometries. For example, the so-called annular geometry, which corresponds to periodic boundary conditions. So there is a lot of interesting physics that we can realize with these long junctions. So why study dynamical solitons, which after all are the topic of my talk? Well, because they're very elusive. Nowadays, it's well established that you can detect kinks in long Josephson junctions. You can do that by looking at the IV characteristic of the junction. But with breeders, things are much more complex. And the reasons are essentially two. The first reason is that breeders are unstable, as I was saying before, so it's hard to keep them alive and probe them. Another reason is that, well, in junctions, you do not actually measure the phase, the phi, but you actually measure the voltages typically, which are proportional to the time derivative of the phase. And these, for a breeder, actually average to zero over a very short time scale. So it's very hard to get some evidence that this oscillation is actually taking place. So that's why we study them, to, in a sense, solve this challenge. But there are other reasons. For example, there can be interesting applications taking advantage of breeders. For example, you can use them to transmit information in these superconducting circuits. You can actually, by going to a suitable quantum regime, you could actually use them as flying qubits. So qubits which perform computations on the go. And essentially, these breeders oscillate at terahertz frequency. And so you could also envision applications for them as terahertz generators. So, you know, and generating terahertz radiation is nowadays quite an important challenge. But, you know, owing to the generality, universality of the sine-Gordon model, we can also look beyond Josephson junctions. These nonlinear excitations, such as breeders, are widely studied in natural systems. For example, they are actively studied in ITC cuprates, in layered superconductors, but also in geological system, in biological system, in DNA in particular. And they're also actively studied in ultracold atoms, for example, with atom chips. And more recently, a study appeared which essentially explored a new kind of sine-Gordon model in robotic metamaterials. In this study, they actually focus on topological solitons, but there is already some interesting activity going on regarding breeders there as well. So with that being said, I will now get into the results, some results. And in particular, I'm going to consider, you know, a sine-Gordon equation in the presence of dissipation, some alternating current, and some Gaussian noise. Now, why do that? Well, essentially, we can imagine this as an AC current, which we applied in the junction, and the idea is to stabilize breeder in the presence of dissipation, because otherwise they would die out. And the Gaussian noise is something that we consider because of thermal fluctuations, which are going to be present in any system at finite temperature. For example, the aim of this investigation is to essentially detect breeders in long Josephson junctions, so we consider some parameters which are somewhat reasonable for the long Josephson junction. And let's say we're going to address both the generation and the detection. So the idea is to start from no initial conditions, so no solitonic degrees of freedom are present in the initial stage of the simulation, and we are going to consider different geometries as well. So the basic phenomenology is the following. So if you consider an AC-driven sine-Gordon system and the noise is very low, what you will see is something like this. So this is an animation showing the phase, different snapshots of the phase as a function of space. And you can see that due to the uniform AC current, you have essentially spatially uniform oscillation of the phase. So no localized excitations are present here. What's very interesting is that if you increase the noise, you may be able to produce these additional localized modes on top of the oscillating background, and these are essentially breather modes. We can say that because their amplitude is essentially equal to the amplitude that you would expect for a breather at that specific frequency. So this would be given by these red horizontal lines in the plot. So we have a way, we are proposing a way of generating breathers which takes advantage of fluctuations plus a deterministic drive. And that's, according to us, an interesting way of having this, of producing these stabilized nonlinear modes. So we studied this phenomenon in more detail, and we defined three, let's say, essentially generation probabilities that we wanted to study as a function of the noise amplitude, or which is the temperature, basically. So this plot shows you probability as a function of the noise amplitude, and the blue curve is the probability of having a uniform background, so no solitonic excitations. The green curve is the probability of having breather modes only, and the red curve shows you the probability of having at least a soliton mode, at least a kink mode. So we evaluate these probabilities over say a large number of realizations, and we plot them. So what we see is that for very low noise amplitudes, we have essentially a probability of say it's zero probability of generating solitonic modes, but then as we increase the noise, we get to this sweet spot here where the probability of generating breathers is very high and everything else is very low. So this range right here is essentially a range of temperature that is optimal for generating breathers which are stabilized through fluctuations. So that would be a good region for performing a breather detection experiment, for example. So we studied the statistics of this phenomenon a little bit and the effect of geometry. For example, for the Neumann boundary conditions, which is the so-called overlap geometry, we observed that the probability of generating breathers is very peaked at the boundaries of the system and is pretty much constant, towards the middle of the system. So we understand that. Oh, by the way, here I'm showing you the number of breathers that we obtained in numerical simulations as a function of space for different noise amplitudes. So what we see is that this generation probability of or counts are strongly peaked at the boundaries, as I was saying, and essentially this is due to so-called edge breather modes. So it's due to the fact that at the boundaries we can have this kind of half breather modes that are very favorable in energetic terms. So we have this kind of weird phenomenon due to boundary conditions. But far from the edges we get somewhat uniform probability of generating breathers. If we take a look at the periodic boundary condition case, well, in that case there are no preferred points, there are no edges, so the generation probability is going to be constant over space. So essentially this is what we see. And you may note by looking at the different colors that by increasing the noise amplitude, so by going from blue to orange, I increase the average number of breathers. So the more fluctuations, the more breathers I get in my system. And that's good. That's an interesting phenomenon. So given that we're proposing a generation approach for having these breathers in a stabilized fashion, can we now devise some experimental approach to detect them? Well, indeed, we tried to. We proposed two different approaches that look at two quite different physical quantities. So the first approach that we proposed is essentially a statistical signature. So we look at the voltages that is produced by breathers in the junction, and we're able to relate this voltage. We're able to put ourselves into a situation where this voltage is an oscillating function, and this period of oscillation is related to the frequency of the breather. So I'm not going to get into too much detail here, but the idea is that we can probe the breather oscillations as voltage oscillations. And yeah, this is quite an interesting experiment that is actually within experimental capabilities of nowadays Josephson labs. Also, we devised a second approach, which is essentially taking advantage of the fact that in thermally biased junctions, so junctions where in which the electrodes are subjected to some kind of thermal imbalance, you know, having a breather in the system can lead you to a local heating. So essentially, in this case, the signature would be a temperature signature, which is very different from the first one. The two approaches are different also because in the let's say voltage approach, we need to destroy breathers in order to detect them, whereas the temperature signature would be a truly non-destructive signature of the bound state. So we would be probing the actual breather mode as it's going through its oscillations. So again, I'm not going to get into too much details. The discussion is quite technical, but for example, you can take a look at this paper right here through this QR code where we go into this voltage business, and there is also a preprint where we discuss in let's say great detail how the temperature signature would work in these thermally biased Josephson junctions. So let's say to conclude, I've discussed about these breather modes of sine-Gordon breather modes, which are also referred to as dynamical solitons because of their internal oscillations. We have seen that these modes are kind of widespread within natural systems. They are studied in many different areas, and let's say we are proposing a way of exciting them in Josephson junction in a controlled way by taking advantage of an alternating drive and thermal noise. And we do that because we want to solve the breather detection problem in Josephson system, which has been open for quite some time now. And so let's say this allowed us, this generation technique allowed us to devise two different strategies for unveiling the properties of these modes in experiments. So I would like to thank you. I would like to thank some collaborators. I'm working, let's say, in the topics regarding sine-Gordon model now in different systems. I'm working, let's say, I'm very grateful to the Palermo group and to my PhD advisors for introducing me to this field of sine-Gordon in long Josephson junctions. I'm also right now studying the sine-Gordon model in ultracold atoms. In particular, I'm very grateful to the folks at ETH Zurich, and also I'm collaborating with this experimental group led by Jörg Schmidt-Meyer. And finally, I'm also looking at sine-Gordon model in layered superconductors. And so we're studying some operant problems in driven qubit materials in the sine-Gordon framework, and it's also very interesting kind of application of the model. So with that, I thank you very much for your attention.
Okay, thank you very much, Duilio. Are there questions, comments? If not, I have two very short questions. First one, when at a certain point you have shown the different geometries of the Josephson junctions, what is is there a direct relation between this type of geometries and the specific models that, or you just have the relation is just in the boundary conditions?
Yeah, pretty much. It's, for example, there are also other geometries, for example, but let's say the main difference is in the boundary conditions. The overall structure of the model is pretty much the same, let's say.
Okay, when you have shown, let's say, one of the most important results about the generation probabilities, the three scenarios are alternative. So, I mean, the sum of these probabilities is one.
Of course, yes.
Okay, and finally, I mean, it might be of some interest to consider multiplicative noise.
That's a good question. Let's say from a general point of view, let's say from the study of the properties of the noisy sine-Gordon model, I think it would be interesting and it could lead to interesting effects. Of course, depending on let's say it depends on what the goal of the study is, I would say. Let's say in our system, the more natural choice is to simply consider some additive noise, which stems from thermal fluctuations. Yeah, but I think it could be interesting for sure to study some multiplicative noise. I think that part of this work has already been even tried to study the stochastic dynamics of breathers in the presence of multiplicative noise. There is some work in that direction. Okay, I see that Bernardo has raised the hand.
Yes, just comment. I agree that in the presence of multiplicative noise, I may expect very interesting rich dynamics because the noise is proportional to the order parameter, and this can be contributed to, for example, to enhance some stability of the breather. Just a comment. This is another comment. Just to Duilio. What is about the quantum breather? I know that you start to this direction. You think in study the dynamics of quantum breather, it is possible to find some similar phenomena that you already analyzed and found?
Yeah, that's another good question. So, yeah, I think in principle it could be possible. It's not something that I'm actually working on, but let's say it would be probably it's a problem. Let's say that should be defined in a sense. Let's say what kind of are you thinking of studying? Let's say the quantum sine-Gordon model in an open system kind of scenario, because it could be. Let's say we should define what we mean by studying quantum breathers in the presence of noise. It's not let's say as I would say as direct as it is for us in Josephson junction. So. I'm pretty sure that some kind of...
Because the system is different. The system is different, of course.
It's a quantum system, so we should define, let's say, in which sense we would like to study, let's say, some noisy dynamics. And there could be different ways of envisioning this problem. That's what I'm saying. I'm pretty sure it could be interesting, and it's possible that maybe some work looking into that is already out there. It's possible that something like this has already been done. Even.
Okay, thank you.
Thank you.
Okay, I think if there is no other question, I think that we can thank again Duilio. Okay, thank you.